In Unit 2.3, we're going to learn a couple more rules as far as our derivative rules go. So like I said in our last lesson, I would really encourage you to make some flashcards so that you can study and memorize these rules. So up until now, we've learned a few different things. We've learned how to take the derivative of a polynomial or a power. So when I have like x to the power of n, so like a quadratic or a fourth degree polynomial. We've also learned how to take the derivative of the sine of x. So I know like the derivative of the sine of x is the cosine of x. We know how to take the derivative of the cosine of x, that is negative sine of x. We've learned our rules for when we have a constant. We have learned our rules for when we have e to the power of x. So not just an exponential with any base, but specifically e. Same with a logarithm with base e. And finally, we learned a couple of rules where what to do if I have a constant times my function, so a constant multiplier, and what to do if I have the sum or difference of two functions. So these are all types of functions where we can take the derivative already. But unfortunately, it does get a little bit more challenging when we have to work with a product. So by product, remember, I mean multiplication, or a quotient. So by a quotient, I mean division, or the chain rule, which is something that we will apply to when we have composition, so composite functions. And we have to be really careful that we do not make up our own rules. It's tempting, but we have to use the actual rules that apply. Okay, so the two rules that we're going to talk about first are the product and the quotient rule. And let's just start with the product rule. So when we take the derivative of a product, so I'm multiplying like my function f with my function g. So if I have a product of two functions and I want that derivative, that means I need to take the derivative of f. So I'm going to multiply f prime with the function g. So not the derivative of g, but its function. And then I'm going to add to that g prime, so the derivative of my second function, with f, my first function. So again, not its derivative, but my first function. And so also remember that addition and multiplication are both commutative. So something that helps me with the product rule is to remember that I'm mixing and matching the derivative of one function with the other function, and then I'm adding those together. And the order in which we do that doesn't necessarily matter. So instead of writing f prime times g, I could think of that as like g times f prime plus f times g prime, because again, multiplication is commutative. Or I could switch the order of the sum, and I could think of like f times g prime plus f prime times g. So as long as we are carefully multiplying f with g prime and g prime with f and adding those together, I think I said that the same, sorry, f with g prime and g with f prime and adding those together, that is the product rule. Okay, so we're going to pause on the quotient rule for a second, and I'm going to come back in another video to go over this proof of the product rule, but let's just come down to this first row of examples. All right, so in this first example, we are taking the derivative of the quantity x squared plus 2, or the sum x squared plus 2, and 3x minus 4. So I could think of that as a product of two different functions. Like my first function is x squared plus 2, and my second function is 3x minus 4. So if you want, you could think of this as like f and g, and you could use that rule above literally. So when I think about taking my derivative here, I usually just kind of say in my head, like, okay, I'm going to take the derivative of my first factor. So the derivative of x squared plus 2 is just 2x. And I'm going to multiply that with the second thing, or the second factor. So I get 2x times 3x minus 4 plus the derivative of my second factor. Well, the derivative of 3x minus 4 is just 3. And I'm going to multiply that with my first factor, x squared plus 2. Okay, so if I were kind of looking at my rule above, I would see that this is like f prime times g plus g prime times f. Okay, so now in order to clean this up, because our derivative on a multiple choice test will likely not be written this way, I would always check to see if I could factor out like a GCF if I have multiple terms first. But since there's nothing to factor, all we could really just do is distribute this multiplication and then see what happens if we need to like combine like terms. So when we distribute, we would get 6x squared, so 2x times 3x, minus 8x. That's my first term, my first two factors distributed. Then we would have 3x squared plus 6. So now when I combine any like terms that I have, well, I have 9x squared minus 8x plus 6. So that is our derivative. All right, I think you should pause the video and that you should try these next two examples, just going across the row, and then resume and see how you did. All right, in the second example, we have x squared times cosine of x. So again, I need to look at this and recognize that I know how to take the derivative of x squared. I know how to take the derivative of cosine of x, but together those are a product of two things. So that's why we have to use the product rule. And again, if you want, you could label this like F and G. Sometimes that's helpful in the beginning when we're first practicing. So to find my derivative, I want the derivative of my first function or my first factor. So my derivative of x squared is 2x. And I'm going to multiply that with g, which is just the cosine of x. Then I'm going to add to that the derivative of the cosine of x. Well, that's just negative sine of x. And I'm going to multiply that with my first function, x squared. And so the only thing we can really do here is just kind of rearrange this. If we were working this out on like a multiple choice style assessment, I think this would be written as minus x squared sine of x. So normally when we write our answers, we will have numbers first, then powers, then exponentials, then trig. All right, this last example, the third example, when I look, I'm like, okay, I see 4t cubed. So I have this first thing where this first function where I know my derivative I could find using the power rule. And then the second thing I have is just e to the power of t. And that's one of my transcendentals that I learned last video. So again, when I take my derivative, the derivative of my first function, 4t cubed, is just 12t squared, times my second function, e to the power of t, plus the derivative of my second function, e to the power of t, times my first function, 4t cubed. So when we go to clean this up, the first thing I would do is write this in the order. So we said if we have a number that usually comes first, then any powers, then any exponentials, then if I had like a sine or a cosine, that would come next. And then I would put my 4t cubed out front. But also we might notice that this, and who knows, like if this is multiple choice, that could be how our answer is written. But it is also possible that we have factored out a greatest common factor. So AP really likes to factor, and not just AP, a lot of college textbooks do this as well, that we like to pull out a GCF when we can. So if I look at my two terms, because remember the product rule always results in multiple terms, I could consider my 12 and my 4. And from those two numbers, I have a GCF of just 4, right? And then I've got t squared and t cubed. So the maximum number of t's I could factor out would be 2 of them. So 2 factors of t or t squared. And then both of my terms have an e to the power of t. So I could factor out e to the power of t. So 4 times t squared times e to the power of t is our greatest common factor of those two terms. And if I divide those terms by the GCF, I'm left from the first term with only the number 3, and from the second term with only the variable t. So by factoring out our GCF, this is another common way that we'll see our answer written. All right, so let's go take a look at the quotient rule. And like I said, this proof of the product rule will be in a different video, more of like an optional watch. If you want to try to follow it in the text on your own, that's fine. All right, so when we get to the quotient rule, now we have to be really careful. This rule is harder than the product rule because our derivative using the quotient rule will involve subtraction and division. And remember, subtraction and division are not commutative, meaning that I can't subtract or divide in any order. So like 2 minus 5 is a negative number, whereas 5 minus 2 is positive. So that's what makes the product rule easier, is that addition and multiplication are commutative. So if I have the product of, or excuse me, not the product, if I have the quotient of two functions, so let's say f and g, and I want to find their derivative, now the order, we have to be really careful. I have f prime times g. That is the same as g times f prime though, because that piece is multiplication and multiplication is commutative. So I have f prime times g, or g times f prime, minus g prime times f. So again, I could think of that as f times g prime. I just cannot switch the terms in the numerator. And then that's all going to be over g squared. So our denominator squared. And so just to reiterate, I could rewrite this as g times f prime minus f times g prime over g squared. When I wrote that just now, the only thing I did was switch the order of these two factors in each term. So the reason I show you it this way is there is a stupid little saying that might be helpful when we're using, when we're finding the derivative using the quotient rule. And I remember learning this when I was in high school, and it has just stuck in my head. It's not clever, it's just catchy. So sometimes we will say low d high, meaning that I'm going to take my denominator, which is the thing on bottom, so that's our low, and I'm going to multiply that by the derivative of my numerator. So that's d high, so derivative of high, the thing on top, or the thing that's high is the numerator, minus high d low. Oops. So high d low, that is, again, our numerator times the derivative of low, the thing on bottom, our denominator, all of that over low. And what I tell my students, and you are my students, I tell y'all to remember to start low, end low. So low d high minus high d low over low. And again, that's kind of silly. It's just kind of a cheat, but it's catchy. It gets stuck in your head, and it could help you remember the quotient rule. Alternately, you could remember the quotient rule because it's just the product rule, except instead of addition, you have subtraction. That's your numerator, and it's divided by the denominator squared. So whatever you have to do to memorize the quotient rule, do it. But do make sure you memorize the quotient rule. Okay, let's look at a couple of these examples at the bottom of this page. So again, as I'm looking at these, I should see that I know how to do like parts of these based on the rules I already know. But what's making it more challenging is that there's now division. And unfortunately, I can't make up my own rules. Because if I could make up my own rules, I would make them easier. Like there's easier fake rules I could make up. So for our first example, we're taking the derivative of the square root of x over the natural log of x. And the first thing I want to do before I even take the derivative personally is rewrite this as x to the x to the 1/2 power over ln of x. All right, so now when we take our derivative, I have low d high, so I have the denominator multiplied with the derivative of the numerator. And we said as far as multiplying those two pieces, because it's multiplication, it doesn't matter what happens first. So that was low d high minus high d low, so minus my numerator, x to the 1/2 power, times the derivative of the denominator, 1 over x. And then all of that is going to be divided by the denominator squared, so low. All right, so we get our derivative, and it's kind of nasty looking, but that was just our calculus step. And now we're done with calculus, but we do need to use some algebra to clean this up. So I notice that I have a term in my numerator that has negative exponents, and then I have another term in my numerator that does not have negative exponents. So anytime I have a derivative or just any function that results in having negative exponents, I'm going to want to rewrite it without negative exponents. So what I need to do first is break up my fraction. I used to work with a teacher here who said uncommon denominate. I thought that was funny. That's kind of what we're doing. We are breaking up this fraction into the difference of two fractions. And for right now, they do have a common denominator. So the natural log, the natural log of x squared. Okay. So all I did was split this into the difference of two fractions. And now I can see that my first fraction has a 1/2 in it. And when I have 1/2 in my numerator, I could think of like multiplying on the top and bottom by 2, but that 1/2 is really going to mean that I have a 1 in the numerator and a 2 in my denominator. I also have x to the negative 1/2 power in my numerator. And so again, I could bring that down to my denominator to have a positive exponent. So now I have x to the positive 1/2 in my denominator. So my first term is the natural log of x divided by 2 root x times ln squared x. All right, when I look at my second term, right now I have x to the 1/2 times 1 over x. And I might need to think about this out to the side, but if I have x to the 1/2 over x to the first power, if I were to subtract, that's really like having 1 over x to the 1/2 power in my second term there. So I could think of this as really being a 1 over x to the 1/2 power. All right. And since that is a fraction, again, like since I've got 1 over x to the 1/2, I could actually keep my 1 in my numerator and bump my x to the 1/2 to my denominator. All right, so now if I go and clean this up, we have ln of x over 2, I'm going to write this as x to the 1/2 power, ln of x squared, minus, we now just have a 1 in our numerator, x to the 1/2 power, ln of x squared. Now when we were working with our negative exponents, that caused us to lose our common denominator, and we want to get it back. So if I look, I really need to multiply my second term by 2. Whatever I do to the bottom, I have to do to the top to get my common denominator again. So now we could put this all over one denominator. We're going to have ln of x minus 2 over 2 root x times the natural log of x, that quantity squared. I also wanted to just make a quick note that when I have the natural log of x times itself, we often write that with the exponent between the ln and the x. You'll see it kind of two different ways. All right, so that was a lot of work. That was a lot of cleanup to get to this final answer. And again, if I'm working on a free response style question, it doesn't matter what form of the derivative I leave my answer in. I could have just stopped in that first line. This very first line we got when we used the quotient rule, that's our derivative. And that's when we were done with the calculus step. But oftentimes when we are trying to simplify for a multiple choice style question, we're going to really have to clean it up with some algebra. And it's kind of gross sometimes. All right, let's look at one more, or also if at any point you want to pause the video and try these next two examples, you may. Just erasing this to get a clear space here. All right, this middle example, again, I'm going to rewrite this before I even start taking the derivative. I'm going to get rid of the radical because we don't have a rule for taking the derivative of a radical. We have a rule for taking the derivative of a power. So I could rewrite the cube root of x as x to the 1/3 power. So now when I take my derivative, again, I'm using my quotient rule. So low d high, so the derivative, so my denominator x plus 2 multiplied with the derivative of my numerator, 1/3 x to the negative 2/3 power. So low d high minus high d low, so x to the 1/3 power times the derivative of what's on bottom, my denominator, x plus 2. Its derivative is just 1, all of that over low, x plus 2 squared. Okay, so just like before, it's kind of gross. We have two terms in our numerator because, again, the product and quotient rule always yields multiple terms. And I can't just take, I can't take my x to the negative 2/3 and put it on bottom right now. Or the 3 from the 1/3, I can't take that and put that on bottom right now because my second term, this x to the 1/3 power in my numerator, does not share those factors. So that's when this happens, that's when I have to break this up into two separate fractions and deal with these separately. Okay, so all right, now that we have separate fractions, I can take my 1/3 from the top, keep my numerator 1 on top and my denominator 3 on bottom. Also, I have x to the negative 2/3 power. I could move that to the bottom of my fraction, make that x to the positive 2/3 power. And it might be tempting right now to cancel out a factor of x plus 2, but don't do it because we're going to want common denominators and we're just going to have to multiply by x plus 2 again. All right, on my other fraction that resulted from my other term in my numerator, there's not a lot to do there right now. So if I clean this up, I have x plus 2 over 3x to the 2/3 power times x plus 2 squared minus x to the 1/3 power over x plus 2 squared. So now that we've dealt with our negative exponents and we got rid of our fraction within a fraction, our goal is to get common denominators. So if I look, these two factors, well, the 3 and the x to the 2/3 power, that's all that changed about my denominator. So that means over here, I need to multiply by 3 times x to the 2/3 power in both the denominator and the numerator, as we do, so that we can change the denominator of our fraction. Okay, so now we have x plus 2 minus, I'm going to combine this under or over the same denominator now. Remember that when you multiply two powers of the same base, you add the exponents. So 3x to the 2/3 times x to the 1/3 is just 3 times x to the first power. All right, so we have x plus 2 minus 3x. And then we said our common denominator is 3x to the 2/3 power times x plus 2 squared. And lastly, I could subtract x minus 3x and get negative 2x. So 2 minus 2x over 3x to the 2/3 power times x plus 2 squared. That's most likely how we're going to see our answer written, that last way. Who knows, sometimes AP might factor a GCF of 2 out of our numerator. We could think of that as 2 times 1 minus x, but I think we are most likely to see that. So typically, remember, we were done with calculus in this first step. Once we take our derivative, we have our derivative. But when we're trying to clean our answer up to find it in a multiple choice style question, that's where a lot of this algebraic manipulation comes in. And I don't want to have negative exponents. I generally want to have a common denominator. I often want to factor out a GCF when I can. All right, let's take a look at this third example. Again, I would encourage you to pause the video and try this one on your own. So if you want to pause, you may do that right now. Or you know what, you could actually pause this video whenever you want because it's a video. That's how they work. All right, so this last piece, again, we want to take our derivative. It is a quotient. So we're taking the derivative with respect to w. So our derivative, we're going to have our denominator, w cubed plus w, times the derivative of our numerator, 2w. So again, that's like a low d high, minus high d low, so my numerator, times the derivative of my denominator, which is 3w squared plus 1. And then all of that over our denominator squared, so w cubed plus w squared. And so I want to point out that when I'm saying low d high minus high d low, again, I am alternating I'm saying g times f prime minus f times g prime. But if you're more comfortable following the quotient rule as it's written, we should still get the same answer because, again, we're just switching our factors in our terms at the top. All right, so now I notice that I don't have any negative exponents to deal with here. I also don't have any like fractions in my numerator, so I don't need to break this up into two different fractions. The only reason we did that, like in this last example, from our original derivative to breaking it up, was to deal with those negative exponents. So here, I'm better off not doing that. And the next thing I might consider is, do I have a GCF in my numerator that I could factor out? But I do not have a greatest common factor of my two terms in my numerator. So all I can really do here is distribute and simplify. So I could distribute 2w to both of those terms. And then over here, we could distribute w squared minus 4 to 3w squared plus 1. All right, so we just want to be real careful when we do this. So we should get 2w to the fourth power plus 2w squared. That was our first term distributed. And then the other thing we want to be really mindful of is this subtraction here. So we either need to distribute that as we go or keep everything in parentheses and do that next. I'm going to leave the subtraction and put this next bit in parentheses. All right, so when we do w squared times 3w squared, we get 3w to the fourth. Let's see, plus w squared minus 12w squared minus 4. All right, that's our numerator. I know it's a pain to keep rewriting our denominator, but we need to. All right, now in my next step, I might distribute this subtraction. And so I could change this to that was weird. I could change this to a plus sign, so plus, and that's going to just change the sign of everything in here. That might be one way to think about it. All right, so now we have 2w to the fourth plus 2w squared minus 3w to the fourth minus w squared plus 12w squared plus 4. All of that over w cubed plus w, that quantity, squared. All right, and then lastly, we just want to carefully combine our like terms. So I have a 2w to the fourth and a negative 3w to the fourth. So that's just going to be a negative w to the fourth power. I have a 2w squared, a negative w squared, and a 12w squared. So that's going to have a sum of 13w squared. And then I've got this lonely plus 4 at the end. And again, all of that is over w cubed plus w, that quantity squared. So when we're going to look for our answer, again, if this was like a multiple choice style question, because if it wasn't, we could have stopped as soon as we took the derivative. I might be looking for a lot of different things. Sometimes my denominator might be factored out differently. I might have a denominator where they factor out a w squared, and it would look like this: w squared times w plus 1 squared, and then the same numerator. I'm just going to be lazy and not rewrite it. So if you ever see something like this and you're curious about the denominator, remember, like w cubed plus w times w cubed plus w, how we could get that denominator is by factoring out a w from each of these factors. So I get w times w squared plus 1 times w squared plus 1. And that condenses to w squared times w plus 1 squared. Oh my goodness. I made a little mistake there. That should have been w squared times w squared plus 1, that quantity squared.